Welcome to the second video in the linear algebra series. I just wanted to mention something that I forgot to mention at the start of the first video, which is that on the first slide you can see my email address. If you have any questions about anything I say in the videos, you can always send me an email and I will try to reply as soon as possible. Now, let's get started on the third topic in my lectures, which is Gauss-Jordan reduction and reduced row echelon form. So let's get started. We first want to motivate a bit why we are interested in Gauss-Jordan reduction before I explain what it is. So we make the following observation. If our coefficient matrix A is the identity matrix I, which is this matrix here with zeros everywhere except on the diagonal where you have ones, and we have that our vector of unknowns x, and our other vector b, they are in Fn, then our linear system of equations reduces to this. So we just have our unknowns and our b's here, and they are equal. So our solution will be x is equal to b. So in some sense, if we can reduce the system to a form where a is close to I, so we have a lot of zeros and only a few ones, it's very easy to obtain a solution. And the procedure of taking our coefficient matrix A close to I, so in quotation marks of course, is called Gauss-Jordan reduction. So to understand more about Gauss-Jordan reduction, we first want to define the notion of reduced row echelon form and row echelon form. So yeah, we need a definition. So this will be quite a long definition, so bear with me. A matrix in Fn by n is said to be in row echelon form if the following conditions are satisfied. So if the rows below a zero row are all zero rows, the leading non-zero entry of each non-zero row is a 1, and finally the number of leading zero entries of non-zero rows increase from top to bottom. So basically, I will show an example of this later. For now, just try to understand what this says, and if you need to reread it again and rewatch this part. So, and it is said to be in reduced row echelon form if it is in row echelon form and the leading one in each non-zero row is the only non-zero entry in its column. So you might be thinking, what is this? So let's look at some examples. So we can consider this matrix and we see that it is in row echelon form. Why? Well, first of all, the first non-zero entry in every row is a 1. The number of leading zeros is increasing from top to bottom. And finally, there's no zero row in this one, but if there was a zero row, then every row below would also have to be a zero row. We can actually take this matrix and reduce it further, and then we obtain a reduced row echelon form. So here we see that we have zeros here also. So that is satisfying this condition of having the leading one in each non-zero row is the only non-zero entry in its column. So, for example, this column only has a 1 here, and this column only has a 1 here, and this column only has a -1 here. Alright, so let's look at an application of Gauss-Jordan reduction. So we're going to balance this chemical equation, which is the oxidation of glucose. So we have these molecules here, so we have glucose, oxygen, carbon dioxide, and water. And the unknowns that we have are the coefficients in front of these molecules. So we set up an atom balance. So we look, for example, at hydrogen. Here we have 12 hydrogen, and here we have 2. And we know that on both sides of the reaction arrow, they have to be equal. So we can say that 12x1 should be the same as 2x4, which gives us this equation for hydrogen. We do the same for carbon and oxygen. And then we obtain this augmented matrix. So you can see here 12x1, 0, 0, minus 2x4, because we move this to the other side and we take our b to be 0. So we do that for every single element. And then we use elementary row operations, and this is the process of Gauss-Jordan reduction. So we're trying to bring this matrix into a form where it is close to the identity matrix, so that it is easy to look at the solution. And what you should recall from the previous video is that using elementary row operations, we do not change the solution of the system. So we can use them to subtract rows and to create more zeros in a way and more ones. So first we perform these row operations and we obtain this matrix. And then we keep going with this and we do a bunch more operations. And I will not go through these in detail now. I might do it in the lecture, but we have to see. Again, so we get more zeros. We do some more, we rearrange some rows here, we swap them, and here we add them again. And you can see here that we create this nice identity matrix block, basically. So what we can then do is we can take this augmented matrix and translate it back into a system. So here we have 1x1 plus 0x2 plus 0x3 minus a sixth x4 is 0. So we can also move this, basically move it here, and then we get this equation. And we do the same for the other rows. And of course x4 is just equal to itself. And then what we can do is we can set x4 equal to 6, because x4 is free, because the only thing it needs to satisfy is to be equal to itself, so it can take any value. And then because we want, of course, an integer number of molecules, we take x4 is equal to 6, so that this equation becomes 1, or x1 is equal to 1, and we obtain this, which is indeed a balanced reaction equation. So yeah, this is an application of Gauss-Jordan reduction, and you can apply this to any system you want. It can be as big as you want, and you can reduce it to a form where you have like a block of an identity matrix and then something else, or just the identity matrix, and you can very easily see the solution. Okay, that is the end of this video. In the next video we will talk about matrix algebra. Yeah, that's it. Thank you for watching.